Hope you had a wonderful break. Ready to jump back into the math. So let's pick up right where we left off. The review, because this is going to be important for where we go next. So we got to make sure, and also for your homework Thursday, these questions are related to the part of the homework for Thursday. So let's see if let's blow the dust off the brain and see if we still remember this stuff. You can work together just a couple minutes. So this is exact rate of change of temperature in a refrigerator. Okay, exact rate of change of temperature in a refrigerator over some course of like 15 minutes. So there's some initial time, 0 minutes. So over some time delay of 15 minutes, we want to look at, answer these questions relative to this. And what do we call that? R sub t, right? So this is R sub t of x. Come on. Okay, so this is, I really thought I was ready. It's not. Okay. This is rate of change of temperature with respect to x, which is time in minutes elapsed in some initial time. Remember that? This is exact rate of change function of temperature in the fridge. Based on that, you're going to answer these 3 questions, which is important for us to get back to where we were and for your homework Thursday. Go. Okay, so I've forgotten my list today, so I'm just going to point and shoot. So here we go. How about in the striped shirt here, right here? Yes, black and white striped shirt.
Oh, it's a dress.
Sorry, I can't see. I can only see the top, so it looks like. No problem. It didn't take that long. Okay, so what do you think about this first function that gives the exact total accumulated changes in temperature? I want the function. We're defining the function that's going to give us this exact total accumulated changes. So what would I write? A sub t of x equals what?
2 interval 0 t or
X.
And then r
of, we need something else, right? So use little c, that's fine. Okay, Michael, agree with that? You agree with that, what you said? Ian also? Yes, sir?
Just get rid of the plus 2.
He wants to get rid of the plus 2. Should the plus 2 be there or not? We want the function to give us the accumulated changes in temperature. Do we want the plus 2 or not?
No.
You're changing now? Don't want the plus 2 for this. Okay. How many got it before we started? Oh, should have been more, but that's at least some, okay? All right, now we want the function that gives the exact temperature in the fridge. Exact temperature. How about white hat, blue shirt? Tell me your name. Yeah.
Gunner?
Gunner. How about number 2, Gunner? Did you get the function for the exact temperature in the fridge?
It's a same function that's above.
Okay. He wants to take just the accumulated changes and add 2 to all the accumulated changes to get the temperature function. That's it. So we'll rewrite it. Last thing here. An expression that represents the change in temperature from 3 to 7. How much did the temperature change between 3 minutes and 7 minutes after the initial reading? Down in the front, Hector.
You do the integral, and then at the bottom you put 3,
Okay.
and 7,
Okay.
and then R to T, T, and T.
Okay. Plus 2. This is what a lot of us missed on the test. And we worked on it that Thursday, right before the test. Plus 2 or not? If we want the accumulated changes in temperature from 3 to 7, do we add 2 to this integral or not? No. Why? Because the changes from 3 to 7 has nothing to do with where the temperature, what the temperature started at. It could have started at 10, it could have started at 2, it could have started at 100. By the time it got to 3 minutes, now we want, starting at 3 minutes, we want the changes, regardless of what that starting temperature at 3 minutes is. So regardless of what the starting temperature at 0 minutes is. Doesn't matter. We don't, so this accumulates changes from 3 minutes to 7 minutes. 3 minutes to 7 minutes, okay? Questions on these questions? Anybody? Okay, so let's just really quick talk about where we've been. Or let's put that in and let's get a number. So what I can do is, I can do Control-Shift-I gives you integral, and we want from 3 to 7. And then R sub T, oops. Let's try that again. R, capital T, there we go, T, D, T, and we get a number. So we talked about this on Thursday before break, that this is what's called an open expression. It's unlike the things you've worked with in the past where you could just plug in a number and punch it in your calculator and it'll give you the answer, like polynomial, right? So this is open. X squared plus e to the x minus cosine of x. This is what we call a closed expression. It just, you plug in a value and it chugs out the answer. Automatic, right? So we just keep putting in x's and we can just get different values. Open means it represents a process, and it's not a quick plug in a number and it cranks out a value for you. So we need the technology to do that for us. Why isn't it? Because it represents the sum of a zillion little changes, right? Accumulated changes. That thing right there is essentially what? M dx. The rate times a little change, a really little change, right? And so we're summing up integral a zillion or a million or a billion, just a lot of little changes. And so that's why we need technology to do that for us at this point. At this point, we need technology to do that for us. So we put it in GC, and it gives us this change in temperature, 1.33611 degrees, between 3 minutes and 7 minutes. And you'll be doing that in your homework as well. Okay? All right, so I think that's good for that. So let's talk about the exam. So the results. Subjects to take a survey. So this would be aimed at students, you're a math major or math education. Okay, so if you're a math major or math education, he would like me to tell you about this survey. It'll take a little bit of time, like 15 to 30 minutes, but you're in the drawing for a $50 gift card. Okay, so if you do the survey, so I will forward this email to the whole class. And if you're interested, he could really use the help on his research study for you to do that survey. So I will forward that email, especially if you're, like I said, math or math education major, this would be great for you to do. Okay? Thank you very much. All right, here we go. So new stuff. So this is spring 2016. Okay, so this is the journey we've been on. What do we say? You know how much of something, you know how fast something is changing. You know how fast a quantity is changing at every moment. Exact rate of change function. You know how fast something is changing every moment, and you want to know how much of it you have at every moment. And we've spent the last month, 5 weeks, working hard on that. And we have arrived. Okay? So you understand that. You understand that process in calculus of you know how fast something is changing at every moment. You want to know how much of it you have at every moment. Okay? So what are we going to do now? We're going to reverse it. Okay? So now, what's our endeavor now? Reverse process. You know how much you have at every moment. And you want to know how fast it's changing at every moment. So given accumulation, exact accumulation, how do we get exact rate of change? What we did. Exact rate of change, approximate rate of change, approximate accumulation, exact accumulation. But notice we just did that, we just reviewed that temperature problem. And what happened? I gave you exact rate. This should be R sub something, R sub F. So just for clarity's sake, our notation, this should be R sub F, right? Exact rate of change, R sub F. Okay? So notice in the temperature, so when I asked you to find those exact accumulation and amount functions, did you have to use the approximate rate and approximate accumulation? No, you just basically, you wrote down those exact functions based on the exact amount function or accumulation based on exact rate. R sub F. So that's what we earned by doing all that hard work on the approximate rate to that approximate accumulation function, that hard equation that we understand now. We earn the right to just take an exact rate of change function and write down the exact accumulation function or the exact amount function. So we paid our dues. We paid our dues because we know where this came from. This is just a more concise version of that long A function, right? That's just a more concise version of the long A function. It still means sum up lots of little changes, m dx, right? And that's what that long A function was based on too. But the point is that we can now, we go right from exact rate of change to exact accumulation. We can just write down the integral function. Okay? So what we're going to do now, exact accumulation that's what we're going to have, and we're going to build approximate accumulation. From that, we get approximate rate of change, and then exact rate of change, and then just like before, our goal is, having understood the process, then we could just write down exact rate of change, a direct kind of streamlined or streamlined process from exact accumulation to exact rate of change. Okay, and this is what we're going to call the reverse process. So whenever the reverse process means you know how much of it you have, you want to know how fast it's changing. That's what we'll just coin the reverse process, since we've worked for 5 weeks on the initial process. Okay. Now the reverse process isn't going to take 5 weeks. It's going to take like a week or 2. It's going to be fast. Why? Because we built all these tools along the way that now we can use. We already have these tools, and so going in the reverse direction is going to go a lot faster. Okay. So let's talk about the area of a square. Area of a square function. Okay? What does x represent in that area of the square function? What does x represent? Do you know? Side length, right? Side length of the square. If you take the side of the square and square it, it gives you the area. So suppose the side length is 6. What's the area of the square? 36. Okay? So it's just like, boom, you got a side length. That formula cranks out an area. But now we have another way of thinking about that. We have another way of thinking about what 6 and 36 means. We can now think about 6 being, or the 36 being, the total accumulated changes in area as the side length changes from what to what? As the side length changes from what to what? As the side length changes from 0 to 6, we're talking about 36 would be the total, not just the final area, but the total accumulation of changes in area as that side length changes from 0 to 6. Does it make sense? So that means we can, now you could write that x squared a different way. How could we write this function, f of x, a different way instead of as x squared? Yes, sir?
2x.
No. So that's something you learned before. So pretend you've never learned anything before this class. We want to rewrite x squared, thinking about it as the accumulated changes in area as the side length changes from 0 to 6. I saw another hand. Yeah.
Would you write it as like the accumulation function?
Okay, so yeah, tell me. So what would that be?
Would you do the integral
Okay.
of like, I had it, but you would put like x on top and then
Okay.
0.
The integral from 0 to x.
Yeah, and then the rate of change of t.
Yeah.
T.
You got it. So if we think of this now, instead of just plug in a side length, crank out an area, we can think of it as the accumulated changes in area as the side length changes from 0 to x. And we can rewrite that function x squared using our integral, right? But so we don't know what the rate function is now. We know that the accumulation is x squared, but we don't know what the rate function is. This is the reverse process. So our new goal is to figure out what the rate function is, right? You know how much of it you have. You want to know how fast it's changing. Does it make sense? So we can rewrite that x squared as an integral of giving us accumulated changes, but we don't know what the rate function is. So here we're going to, that's this process, and the reverse process that we're embarking on now. Okay, so here is that function, x squared. It's the easiest parabola there is, right? The easiest parabola there is. But we're thinking about that independent variable as side length, and then the dependent variable as corresponding area, but we can just think of it as accumulated changes in area as the side length changed from 0 to x. Okay, so what's the first step in the process? We've got exact accumulation. We're going to do what first? If we're reversing what we did before, approximate accumulation. Okay, so what kind of function pretends to be an exact accumulation or amount function, but with constant rates of change? That's what we want. We want a function that pretends to be this one, but has constant rates of change. Okay? Just think more like the graph. We're just going to think of like, what would the graph of that function look like? Okay. Like this? What do we think? Does this simulate the exact accumulation function with constant rates? Talk about this. Does this do the job? Go, talk. What's going on here? Okay, just don't look at this or read it until we give you instructions. Focus on the task at hand. Let's turn it over. Don't do it. Thanks. Let's hear your thoughts about this. Yes or no? Is this how we're going to approximate the accumulation function with constant rates of change? Any comments? Yes. What do you think? Who said yes? Why yes? Okay. Other thoughts? Yes, sir. No. Okay, we have yes and a no. Why no?
I don't really know what you have there that doesn't really represent very much. If we wanted to represent exact rates of change, we have to connect points in the line in a straight line.
Okay, so you want to do that kind of what we talked about that was on the test. Connect points on the curve.
Yes.
Yes, sir.
I also believe it's now hard only because a rate of change is equivalent to dy dx.
Okay.
So what I believe is that it should be the area under the curve.
Okay, so we never talked about area under the curve. That's from a previous class. Try to erase that. We'll talk about area at the end of the course. Area under the curve. Other comments? So let's just look at one of these. Look at this right here. What does that represent? A constant rate of change? Constant. Yeah, a constant value of what? Area of the square of 1. It looks like 1, right? Yeah, because here at when the side length is 1, the area is 1. So this is saying this approximate, or this blue segment right here is saying hold the area of the square constant at 1. So what kind of rate of change do you get? If you hold the area of the square constant at 1, what's the rate of change? Remember, the red curve is not a rate of change curve. The red curve is amounts, or accumulation of area. What's the rate of change here? It's just holding the area steady for increasing side length from 1.5 to 2. So if we're going from approximate accumulation to approximate rate, how is this going to work out for us? What's our rate of change graph going to be? It's going to get 0. We're basically, the rate of change is going to be 0 the whole time. Do you see? Yeah. Yeah, sure. No, vertical line won't. That will say the area is changing when the side length is not changing, right? So you're holding the side length constant, and then the area is going to increase. So that's like impossible, right? So that won't work. Okay, so the reason I'm spending some time on this is hundreds and thousands of calculus students throughout the ages have come to an exact accumulation function, and to make the approximate accumulation function did this, because they're so used to working with rate functions. And to get the approximate rate function, we make a step function, right? And that would have different constant rates. But when you do the step function on an accumulation function, you just get a constant. Your rate of change is 0 the whole time. Do you see it? There's no change in y. There's no change in y for any of these to calculate a rate of change. The changes in y are all 0. So you just get constant rate. You just get 0 rate of change. So it's a different animal. Okay. So when you start with an accumulation function or an amount function, you're not going to build a step function off of it. You're not going to build a step function off of it. Okay. Instead, what are we going to do? So we need constant rates of change in such a way that's trying to mimic the exact accumulation function. Yes, ma'am. Straight lines. So that's what he also said. Yeah, exactly. Okay, so we want a piecewise linear graph with line segments whose endpoints are on the curve. So we're trying to reproduce the curve, but with straight lines. Okay? So something like this. So this has a large delta x here. My delta x is 1, but just so you can see all the daylight between it. Okay? So now this blue curve, or blue lines, the piecewise linear function, trying to be the exact accumulation function, expressing it with constant rates, right? Because the linear pieces each have a constant rate. So constant rate of change over each interval, right? A constant rate of change over each interval. Don't make a step function out of an accumulation function. It doesn't make sense. It doesn't make sense, although scores of calculus students in the past have tried to do it, okay? This makes sense, right? Because now we've got constant rates that are trying to be like the accumulation function. Yeah. What happens with smaller intervals? So here's smaller intervals. Here's 0.5. What just happened to the approximate accumulation function? Got better, right? It's looking a lot like the exact accumulation function. See that? Same principle that we've seen before. Smaller intervals means better approximation. Constant rate of change. A different constant rate of change on each interval. Okay, so let's find these. We've got the function. So these endpoints are going to be crucial. Why? Because they're the link. These points that we use to form those segments. Those are the link from the exact accumulation to the approximate accumulation. That's how we're going to build the approximate accumulation out of these points that we're using as the endpoints of the segments, because they're on the curve and we have information about those points. So what I want you to do first is, you got 1, 2, 3, 4. You've got the function. You can generate values with the function. I want you to find those 4 constant rates of change for the blue approximate accumulation function. Find those constant rates of change. Go. Okay, we'll call them M1, M2, M3, and M4. How do you calculate constant rate of change? And then do it 4 times. So some people are your eyeballing y values. You're eyeballing y values off the y-axis, which is okay, but we can do much better than that. We can get these y values exactly to get our changes in y, right? So m is going to be change in y over change in x. So we're really looking at like moments now. So because we're looking at moments, rather than dx, we can talk about delta x, right? Because we still think about our moments that we've set, we've fixed those. So instead of dy over dx, we can say delta y over delta x, okay? But the principle is the same, the idea is the same. If you have dy over dx, that's fine. But so dx is easy. For all of them, dx is 0.5. That's all of them have a change of 0.5. But how are we going to get the change in y exactly? Not by eyeballing from the y-axis, like looking at the points and trying to eyeball what the values are. We want to get the change in y exactly. So change in y is going to be for M3 is going to be, how can we represent it? Let's see, how can we represent it? How about in the black shirt? How could I represent the change in y exactly? What expression could I write here? So for M3. Excellent, right. She said f of 1.5, that's the final y, minus f of 1. And we know what the f function is, so we've got a closed form, right? Closed form means any side length, boom, we can get an easy area fast. It's a closed form expression, x squared. So f of 1.5 is 2.25. F of 1 is change in y over change in x. Is it 2.5? So that's M3. That constant rate of change that we're using to simulate that part of our exact accumulation function has a rate, that's rate of change of 2.5. Starting from a y initial of what? So in that moment, from 1 to 1.5, what could we say as like y initial or y start? How could I represent it? In that moment, what's my y initial? Oh, I didn't think that was that hard. Let's see. How about here in the blue shirt? How could I represent y initial in the third moment from 1 to 1.5? My starting y value. F of 1, which is? We'll just leave it at f of 1. We know that f of 1 is 1, right? 1 squared is 1. Okay, so what we want to do now is we want to write this piecewise function, right? So we're going to have 4 pieces. There's going to be 4 lines to it. 1, 2, 3, 4. We're going to have 4 lines to it. And so let's just start right with the third one. So we'll start right here in line 3. So thinking about x increasing through this interval, and we want to get all the corresponding y's on our blue segment. So think of x increasing through this interval. So x is changing through the current moment from 1 to 1.5, and we want to represent all the associated y values or for our approximate accumulation function on that blue segment. We've got y initial, we've got the rate of change. Can you do it? So work on the third line in this accumulation function. So that's x going from what? 1 to 1.5. Can you write now what is the expression that calculates all those y values on our blue approximating segment? You got y initial, you got the rate of change. Can you write the expression for every y value given an x value in that interval? Can you do it? Go. Important principle that we worked on. Here. Maybe this will help. Hopefully this, what I'm drawing here will ring some bells. I'm going to call on somebody in a minute. Who remembers? Who remembers? We worked on this. We've seen it repetitively in the last couple months. Okay, let's see. Adrian, did you get it? I'm sorry. What's the first letter of your name? Are you Ricardo? Oh, sorry. Okay.
I think I have it.
Tell me.
F of x minus f of 1.
Okay.
F times 2.5.
F of this times 2.5?
No, f of x.
No, not quite. So we're trying to get what? We're trying to get this y coordinate of this point for some x in that interval, right? We think of x increasing through that interval. And we want to get a of x in that interval. Let's see. Volunteer. Who thinks they got it? Yes, sir. 2.5 dx. 2.5 dx. What would 2.5 dx give us? So m dx. So here's dx. So 2.5 dx is part of it. What part of it is it? Yeah. Okay, so, right. So the 2.5 dx would be the change in y. That would be this part right here. This would be the 2.5 dx. But does that give us the y coordinate of the final value of the point? We also need y initial, right? So it's going to be y initial plus, in general, the y initial plus change in y. Remember that? Y initial plus the change in y gives us the final y. And what is the change in y? M dx. 2.5 times. Now we want x. We want to do it in terms of x, not dx. So 2.5 times what? What is dx in interval 3? In interval 3, what is dx? Do you know? Not 0.5. It could be any, right? So dx starts from here and it increases here, like this. X minus 1. The dx is final x minus initial x. Final x is x, initial x is 1. So initial y plus the change in y, where the change in y is m dx. TAs, have we worked on that this semester?
Not a lot. We did it in the review session for sure.
No, the change in y plus initial y plus the change in y? Yeah. A lot. We've done this a lot. Final y is the initial y plus, that didn't work out so well. Initial y plus the change in y. Initial y plus the change in y. The initial y is f of 1. The change in y is our rate of change times the change in x, which would be x minus 1. Okay, so for homework, you'll finish that function. We want to move on today, but you're going to finish this approximate accumulation function, which will be really easy now, because now you're just going to kind of copy and change the numbers, but try to remember that. Try to remember, this is how we do a piecewise linear function, one piece at a time. Okay, any questions on that? Hopefully that at least rang a bell. And hopefully at least some of you got that before I started. Questions? Okay, so now we want to do this generally. We want to come up with a general function. Okay, so I took the numbers off the axes. So a couple warm-up questions. What kind of function is displayed by the red graph? So this is necessarily the area function anymore. It could be anything. What kind of function is displayed by the red graph? Let's see here. Right here. White shirt and glasses. What kind of function is that? He wants exact accumulation function. Got it, okay? What about the function is displayed by the blue graph of linear segments? Right here in the red shorts. What kind of function is the blue one in general? He wants approximate accumulation. That's it. That's what we just did, right? That's what we just did, okay? So for every x value now, we want the associated constant rate. So here we're after now the constant rate. We want the associated constant rate. We just talked about building the accumulation function. Now what about the constant rate for every x value in the current interval? So let's make that x right there. And then, so we're in this kind of like the second interval. But this could be any interval. It doesn't have to be the second. It could be the fourth, the 10th, doesn't matter. And we want to build the associated constant rate out of the function f, right? So it's going to be all about the function f in this current interval, okay? And so we know that that constant rate is going to be delta y over the change in y over the change in x. We just did that, right? Okay, so our approximate rate function is going to have this general structure. The rule for the rate function is going to be change in y over change in x because it's giving us rate of change, right? It's giving us rate of change. So what change in y and what change in x are we talking about? So looking at this picture, what change in y and change in x are we going to use, just in general? What change in y and change in x are we going to use? Generally. Yes, sir?
The change in x will be dx, so from left x to where x is now, at the beginning of the interval, and then left x.
But to get, we want it, not a bad idea, but we want to get this constant rate, and we need the function, we're going to use the function f to get it.
Okay.
So if we do that, we don't know what that point is because it's not from the function f, do you see?
Okay.
So what would it be instead? Instead of using from the left side to x, we're going to use, what change in x are we going to use? We need to take information from the original accumulation function, f. So where are our reference points, right? To use the original accumulation function f in order to build the approximate accumulation function, these linear segments, has to come from the function f. So what change in y and change in x are you going to use? Just like you did in our square example. Which final and which final and initial? Yeah. Of the right. Yes, right. So we're going to use the starting and ending point of the line, right? Because that's where we have information from f. In between, we don't. They're apart. We don't know anything about what that should be in between, but we know that they cross right there. So at those points, we can take information from f and build a. Right? You can take information from f and build a. Okay, and so likewise, that'll be our change in y. So we need to get change in y over change in x. We need ordered pairs, right? So we're going to need the ordered pair for the initial point in that moment, and the ordered pair for the final point in that moment. So here's where we find out if we can do it. So this is any delta x, it could be any interval, any moment. It could be the second moment, it could be the 8th moment, it could be the 20th moment. How do we express those ordered pairs? The ordered pair at the beginning of the current moment and the end of the current moment. Go. Can we do it? coordinates of the initial point, left x, f of left x. Left x, f of left x. So what's the x coordinate of the final point? So left x takes us to the start, and then we go an additional delta x over. So that x value is left x plus delta x, and then f of that. Now, so the rate function then is going to be the change in y over the change in x. The change in y is going to be y final minus y initial over change in x. So this is our approximate rate function. This is our approximate rate function. F of left of x, the final y minus initial y over the change in x. Delta y over delta x. Should make sense. Okay, so then the function a. We want to write the function a, the approximate accumulation function, by writing the definition of linear segment in, because that segment could be any segment. This formula works in every moment. It works in every moment interval, right? Because when we move into another interval, left x gives us the right, it gives us the x value at the left side of the current interval. So as x increases through the intervals, this continues to spit out the constant rate that we need, right, for the current interval. So now we want to write the function a. What's the definition of the linear segment? We did it earlier in class. Who can do it? So do it. A of x equals what? So you're going to write, how do we get y values on this segment? How do we get y values on this segment? We just did it a little while ago, so hopefully everyone can write it down. Quick, do it, go. Okay, what's going to be the general structure of this formula? Let me see. How about in the working hard, in the Arizona State t-shirt? Yeah. Yes, yeah. What's the general structure of it going to be? That the final y equals? Final y value equals? General structure first. General structure of this. General structure of this formula. Somebody please know it. I know that you know it. Yes?
The change in y times the rate.
You're thinking the right thing, but it's not right. Yes, sir?
Initial y plus the change in y.
Thank you. Initial y plus the change in y. Initial y plus the change in y. What's the initial y? F of left of x. What's the change in y? This times the change in x, which is x minus left x. Initial y plus the rate times the change in x, or the change in y. But that rate is this, because this accumulation function has to be entirely based on f. Right? So what goes there is this. Right? So that expression would go here, and then the whole expression is based on x and f of x, and we've got, look, we already have the approximate rate function in one day. So we did approximate accumulation, and we already got approximate rate in one day, because we had the tools that we needed. Okay, ask me on your way out if you have. This will be part of the homework for Thursday.